about the invisible magic that's happening inside your computer right now. It's the thing that makes everything feel so incredibly fast and responsive, and today we're going to pull back the curtain on it. I mean, seriously, have you ever stopped to think about it? You're typing away, and almost instantly, a little red line pops up under a typo, all while the autosave feature is quietly working in the background so you don't lose anything. How on earth can one single program do all of that at once without just freezing? Well, the answer, the absolute secret sauce to all of this, is a powerful idea called multithreading. It's the technique that lets a single program juggle multiple tasks at the same time, giving us that smooth, seamless experience we totally take for granted. Okay, so to really get multi-threading, we first need to understand its two basic building blocks, the process and the thread. Now, they sound pretty similar, but trust me, they play very, very different roles. Let's break them down. First up is the process. A process is, well, it's the big picture. When you double click an icon to launch an app, you're starting a process. It's the whole container with its own dedicated memory and resources. Think of it like a whole restaurant, the building, the kitchen, all of it. Now, inside that restaurant, you've got your individual workers, right? That's what a thread is. It's a smaller, nimbler unit of work that happens inside the process. So in our restaurant, one thread is the waiter taking an order, another thread is the chef cooking the food. They all work inside the same restaurant, sharing the same kitchen. And this right here really breaks down the key differences. You see, processes are isolated. They have their own separate memory, like two different buildings. But threads, they all live together inside one process. And this is the crucial part. They share memory and resources. Because they share, it's way, way faster for the computer's brain, the CPU, to switch its attention from one thread to another. That's what a context switch is, and that's what makes threads so incredibly efficient and lightweight. So you might be asking, why do we bother with all this? Well, because this whole approach of using lightweight, sharing threads, gives our software some serious superpowers. And the benefits are just huge. We get that amazing responsiveness, right? Your app never completely freezes just because one little part of it is busy. You can click on things with one thread while another is doing some heavy lifting in the background. And with today's multi-core processors, different threads can literally run on different cores at the exact same time. It's just a much, much more efficient way to get more work done. Okay, so we know what threads are and why they're awesome. Let's peel back another layer and get a little more technical. We're going to look at the two main ways threads are actually managed, at the user level and at the kernel level. So on one hand, you've got user-level threads. These are managed entirely by the application itself. The main operating system doesn't even know they exist. This makes them super fast to create and manage. But, and this is a huge but, if one of these user threads gets stuck waiting for something, the entire application just freezes. That's called blocking. On the other hand, you have kernel-level threads. These are managed by the operating system directly. They're a bit heavier, but they're way more powerful. If one kernel thread blocks, the OS can just schedule another one to run. And, most importantly, the OS can spread them out across multiple processors. So we have these two types of threads, right? One the app knows about, and one the OS knows about. The big question is, how do they actually connect and work together? Well, that's all about how they are mapped to each other. The first way to do it is the many-to-one model. This is where an application can create tons and tons of its own user threads, but the operating system only sees one single kernel thread for the entire program. It's efficient, sure, but it has that fatal flaw. One little thing gets stuck and the whole show grinds to a halt. Not great. Then you've got the total opposite, the one-to-one model. For every single user thread the app creates, the operating system creates a matching kernel thread to manage it. Now this is powerful. This is what allows for true parallelism, letting different threads actually run on different processor cores at the same time. And finally, there's a kind of hybrid approach, the many-to-many model. This one tries to get the best of both worlds. It maps a whole bunch of user threads to a smaller, more manageable group of kernel threads. It's flexible, and it avoids that big blocking problem of the many-to-one model. Okay, so with those three options on the table, which one do you think powers the device you're using right now? Which model really has the power and stability that modern computing absolutely demands? And the winner is the one-to-one model. It makes total sense, right? In an age where even our phones have multiple processor cores, the ability to take full advantage of all that hardware is everything. The one-to-one model lets the operating system intelligently schedule threads across all the available cores, squeezing out every last drop of performance. So we've gone through the what and the how, but let's wrap this up by focusing on the most important part. Why does any of this actually matter to you? Where does all this complex, behind the scenes stuff show up in your day to day life? The simple answer is everywhere. That web server delivering this content to you right now, it's using threads to handle thousands of users at once. Your web browser, it uses a different thread for each tab, which is why one slow, junky website doesn't freeze up your entire browser. From online banking to video games to your word processor, multithreading is the invisible engine that keeps our digital world running smoothly. You know, multi-threading was the big answer for how to use multi-core processors effectively. But as we start looking at chips with dozens, maybe even hundreds of cores, the challenges of managing all that power are just going to get bigger.